Today we'll look at the first law of thermodynamics, and this is basically a statement of the conservation of energy for a thermodynamic system. So this law states that the internal thermal energy of a system is equal to the heat going in or out of the system plus the work done on the system by the surroundings, or vice versa. So Joule conducted an experiment and found that the internal energy of a thermodynamic system is dependent purely on the temperature, or the internal thermal energy. And this is basically obeyed approximately for a real gas, but assumed to hold for an ideal gas. And we'll look at Joule's experiment in subsequent videos to show that. So that means if the temperature of the system does not change, then the change in internal energy is zero. Now, a common model of a thermodynamic system that is looked at and studied extensively is shown over here, where we have an ideal gas confined in a container which is sitting on a heat reservoir, and this heat reservoir can add and remove heat from the system. And on the sides we have thermally insulated walls, so heat can only be exchanged between the system, which is the ideal gas, and the surroundings through the heat reservoir. And we have a frictionless piston that moves up and down, and that does work on the gas basically. Now, as we know, the state of an ideal gas is determined by the known state variables, which is pressure, volume, and temperature, and these are related by the equation of state, which you'll be familiar by now. So pressure by volume is the number of moles of gas by the universal gas constant by the temperature. And basically we're going to perform different experiments on this gas and observe changes in the state variables. So for example, when we add and remove heat from the system, or push the piston down to do work on the system and compress the volume, and vice versa. And we're going to carry out these processes such that the system and the surroundings, so the surroundings include the piston and the heat reservoir, and these are going to be in thermal equilibrium each time we carry out a process. So for example, if we look at this pressure volume diagram, so suppose the gas starts from state A, which has some pressure and some volume. And we take the gas through several processes to arrive at state B. So that has another pressure, and the container has another volume in this state. So basically what we do is apply the different processes gradually, so very slowly, such that the system and the environment are always in thermal equilibrium. Okay, so we apply these processes piecewise. So for example, by reducing the force on the piston slightly, such that the volume expands by a small amount, and the system is not disturbed significantly. So in that case, if we apply these changes to the system slowly, so just keep reducing the force due to the piston, we get an expansion in volume, and at each stage the system is going to be in thermal equilibrium with the surroundings, so we don't disturb it much, and you end up at state B gradually. Well, in that case, we can apply the same processes in reverse and arrive at state A. So therefore the process is reversible if we ensure minimal disturbance to the gas. And I'll see you in the next video.